You've seen it in countless movies. A crowd of people firing guns into the air in celebration, or a character shooting straight up at the sky in frustration or warning. Then later, maybe in the same scene or in a different movie entirely, someone gets struck by a falling bullet and drops dead instantly. The implication is clear. What goes up must come down. And when it does, it's just as deadly as when it left the barrel. It's a dramatic moment that feels logical enough that most people accept it without question. After all, gravity pulls everything back to Earth eventually, so why wouldn't a bullet fall with the same force it had going up? But here's the thing. Physics doesn't work the way Hollywood suggests, and the reality of what happens to a bullet fired straight up is both more complicated and more interesting than the movies let on. The key to understanding this phenomenon lies in recognizing that a bullet's journey can be divided into two completely different phases: the upward journey and the downward fall. When a gun fires, the explosion of gunpowder creates an enormous amount of pressure that propels the bullet out of the barrel at incredible speed. Depending on the weapon and ammunition, this muzzle velocity can range from around 120 meters per second for a small handgun to over 900 meters per second for a high-powered rifle. That's faster than the speed of sound. This initial velocity is what makes bullets so dangerous. They carry tremendous kinetic energy concentrated in a small, dense projectile. But once the bullet leaves the barrel, it's no longer being pushed. It's simply coasting through the air, and from that moment on, two forces are working against it: gravity pulling it back toward Earth, and air resistance slowing it down. As the bullet travels upward, air resistance continuously drains its speed. The faster an object moves through air, the more drag it experiences, and at the velocities bullets travel, this resistance is significant. By the time the bullet reaches the peak of its arc, assuming it was fired perfectly straight up, its vertical velocity has been reduced to zero. For just a brief instant, it hangs motionless in the air before gravity takes over and pulls it back down. This is where the second phase begins, and this is where the physics gets interesting. The bullet is no longer powered by gunpowder, it's simply falling, and falling objects don't accelerate indefinitely. They reach what's called terminal velocity. Terminal velocity is the maximum speed an object can reach when falling through the atmosphere. It occurs when the force of air resistance pushing up against the object equals the force of gravity pulling it down. At this point, the object stops accelerating and falls at a constant speed. For a bullet tumbling through the air, terminal velocity is much, much lower than its muzzle velocity. Studies and experiments have shown that most bullets reach terminal velocities between 40 and 90 meters per second when falling. That's roughly 10 to 20% of the speed they had when they were fired. A bullet falling at terminal velocity still carries energy and can absolutely cause injury, but it's nowhere near the lethal force of a bullet traveling at its original speed. The difference in danger comes down to kinetic energy, which depends on both mass and velocity. Kinetic energy increases with the square of velocity, meaning that even a small reduction in speed results in a massive reduction in energy. A 9mm bullet fired from a handgun might leave the barrel at around 350 meters per second, carrying over 500 joules of energy. But when that same bullet falls back to Earth at terminal velocity, around 70 meters per second, it carries only about 50 joules. That's still enough to hurt someone, potentially even enough to break skin or cause bruising, but it's far less likely to be fatal. Compare that to hail, which falls at similar speeds and occasionally injures people, but rarely kills them. The physics are similar. A small, dense object falling at terminal velocity can hurt, but it doesn't have the penetration power of a fired bullet. However, and this is crucial, this only applies if the bullet was fired perfectly straight up. In reality, achieving a perfectly vertical shot is nearly impossible. Even a slight angle changes everything. If the bullet is fired at any angle other than straight up, it retains some of its horizontal velocity throughout its flight. Air resistance still slows it down, but not as dramatically as it does for a bullet traveling straight up and falling straight down. A bullet fired at an angle follows a ballistic arc, and when it comes down, it can still be traveling at several hundred meters per second, depending on the angle and the distance traveled. In this scenario, the bullet can absolutely be lethal. This is why celebratory gunfire is so dangerous. Most people aren't firing perfectly vertical shots. They're firing at angles, and those bullets come down with enough speed to kill. There have been documented cases of people being killed or seriously injured by falling bullets, particularly in regions where celebratory gunfire is common. Studies from places like Puerto Rico and Los Angeles have recorded injuries and deaths from bullets fired into the air during celebrations. Most of these cases involve bullets that were fired at angles, not straight up. The bullets maintained enough velocity to penetrate skin, bone, and vital organs. In some tragic cases, people have been killed while standing on rooftops or inside their homes, struck by bullets that came through windows or thin roofing material. These aren't Hollywood myths, they're real tragedies rooted in physics and poor judgment. Another factor that complicates the situation is the shape and stability of the bullet during its fall. A bullet fired from a rifled barrel spins rapidly, which stabilizes its flight and allows it to maintain a nose-forward orientation. This aerodynamic shape minimizes air resistance and maximizes velocity. But once the bullet reaches its peak and begins to fall, it often starts tumbling. A tumbling bullet has much more surface area exposed to the air, which increases drag and lowers terminal velocity. This tumbling motion is part of why falling bullets are generally less dangerous than fired bullets. They lose their aerodynamic advantage and fall more slowly. However, if a bullet somehow manages to remain stable and fall nose first, its terminal velocity could be higher, making it more dangerous. The exact behavior depends on the bullet's design, weight, and the conditions of its flight. The question of what happens to a bullet fired straight up is a perfect example of how intuition can mislead us. It feels like the bullet should come down with the same force it had going up, because after all, it's the same object and gravity is pulling it back with the same strength. But physics doesn't work on feelings. It works on forces, velocities, and energy transfers. The bullet loses most of its speed on the way up due to air resistance, and when it falls, it's limited by terminal velocity. The result is an object that's still dangerous under certain conditions, but nowhere near as deadly as a freshly fired round. Hollywood exaggerates for drama, but the real science is more nuanced and ultimately more interesting. This distinction also carries an important lesson about how we think about danger. Just because something isn't as lethal as movies make it seem doesn't mean it's safe. Firing a gun into the air is reckless and illegal in most places, and for good reason. Even if the bullet is fired perfectly straight up and comes down at terminal velocity, it can still injure someone. And since almost no one can guarantee a perfectly vertical shot, the risk of firing at an angle and killing someone is very real. The physics may soften the impact compared to Hollywood's version, but the consequences are still severe enough to take seriously. So the next time you see a movie scene where someone fires into the air and a falling bullet later kills someone with pinpoint accuracy, you'll know the real story. A bullet fired straight up will slow down, stop, and fall back at a much lower speed than it started with, making it far less lethal than a fired shot. But if it's fired at any angle, or if someone is simply unlucky, the danger is real. Physics may not be as dramatic as the movies, but it's far more reliable, and understanding it can mean the difference between myth and reality, between caution and tragedy. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution.